Okay, let's talk about Coulombs Law. Coulombs Law. Okay, so Coulomb was a French scientist, and somewhere around 1780, he was experimenting away with charged objects. Okay, so his experiment looked something like this: hang a couple of pith balls of equal charge, so same type of charge, or maybe they might not even have been pith balls. It's possible that they were like metal balls. So let's just imagine what's going on here. So let's say we take a couple of strings, right? We hang some light, like maybe some like tin foil or gold foil balls off of them. It's very light balls that are, say, coated in metal. Okay, right? We hang them side by side on like silk threads. Okay, and now we charge them by induction. Okay, so we charge these balls by induction. So let's say we bring like a charged amber rod that we've rubbed with silk, say, and we come in here. All right, we know that when the charged rod gets close to the balls, the electrons in the balls will be shifted over here, right? Since they're metal, they pull over to the side. We could then ground this out, okay, which will cause, since the negatives have moved over there, that remains or leaves behind a positive on this side. Electrons will move in, and what we could end up doing with these is we could end up charging them both negatively, okay? So then we remove the ground, and we're left with this scenario. Just do a little redraw here. Where both of these will then be charged negatively. Okay, so they'll both be charged negatively. Let's say they're fixed up here on the ceiling, or they could be fixed to one point, like in this drawing, whichever. Actually, I think they do need to be fixed to one point. So let's just correct that a bit. See if we can make it just a little bit more correct. So they're like that. Well, we know from past experiment that when two objects are like charged, there's a tendency that they will repel from each other, right? So you're going to have some repulsion here. So what will happen then is these will move off. Okay, move off to the sides, and you'll get some separation here. So Coulomb was able to work out how much force you're getting here. I'm struggling here to make this happen. Okay, how much force you're getting here, how much repulsive force you're getting based on how much charge has been applied to each of these balls. Okay, so that's kind of the gist of his experiment. I would suspect that, he had sort of a theory about how this would work. Let's talk about that in a minute. Okay, so you have this motion. You now have some angles you can work with. If you know the mass of these balls, right, you can sort out some Fg. Then you can figure out the tension. And through some component method manipulations, figure out exactly what the magnitude of the force here is. We'll call that Fe. All right. What he was able to come up with, first of all, was a couple of relationships. The first thing is this: the electrical force is going to be proportional to the charge on each of these balls. Okay. Now, in the case that we did, these would have equal charges on them, right? Because the charge will separate as far apart as they can and equally distribute. Like back when we were like this, will equally distribute across each of these balls, so they will have equal charges. However, they don't necessarily have to have equal charges. Okay, it will work without. So Coulomb found that the force is proportional to the size of the charges in terms of Q. call this the amount of charge. And he also found that much like with the universal law of gravitation, the strength of the electric force decreases at a square to distance. Okay, and again, that's a property of the way that fields expand out into space. Okay, at various radii away from the center, the area of space that that field has to go through increases at a square to distance, right? The way to think about that is like the size of the shell or the surface area of a sphere as radius goes up. Okay, so area of a sphere is obviously proportional to the square of r. And that's where you get this from, right? If this is your, say, positive charge, those field lines cut through a large area of space, or the field is less dense at a square to distance. So field is less dense by a square of r. And so from these relationships, Coulomb's law was born, which looks like this. Fe equals K Q Q over r squared. So you'll note striking similarity to the gravitational force, right? And we know from past experience that electrostatic force or electromagnetic force and gravitational force are two of the four fundamental forces. So it's not quite all that surprising that you'd end up with these similar types of laws for each of those, two types of force, which are in some way related in that they both permeate the universe and influence all the things in it. Okay, so now we need to talk about what these values mean. Okay, so we've already covered that this is charge, but how is charge measured? Okay, and this is the distance between these two charged particles, right? Okay, negative and positive, or both negative. Okay, and what that's going to do is influence the direction of force. But we measure this distance in meters. Okay, so let's cover the Q first. So Q, and you've probably seen this before, Q is measured in a unit called the Coulomb. Sort of like how force is measured in newtons, I guess. Q is measured in Coulomb. So what is a Coulomb? Well, a Coulomb is an amount of charge. All right? And we have to realize, if we're going to nail down what a Coulomb is, that charge is carried by one of two fundamental particles, either the electron or the proton. Okay? Both of these carry the same amount of charge, but that charge behaves oppositely. Now we, define these as negative and positive. Negative and positive are just names we've given them. It was probably equally likely that they could have been called red and black, or up and down, or whatever. Yes and no. These are human constructs. There's nothing inherently positive about it. It's just a name we've given it. So, so how much is a Coulomb? Well, 1 C of charge is equal to, this is going to be a crazy number, is equal to the number of electrons or protons. Wait a minute, that sentence doesn't make sense. No. Sorry, let me fix this. Carried by, there we go. That's C, that's the symbol for Coulomb. 1 Coulomb of charge, let me read it slowly, is equal to the charge carried by 6.25 times 10 to the 18 elementary charge carriers. All right. So the elementary charge, right? The elementary charge then is the amount of charge carried by a single proton or electron. Okay. So we call that just E. E is the elementary charge. Oh man, that's terrible writing. Cursive. So if it takes this many electrons or protons to make up 1 Coulomb, you might say why this amount? And we'll tackle that in a minute if we can. Well, then the amount of charge carried by each one, right? If that's equal to 1 Coulomb, then each one of these things is, contributing 6.25 times 10 to the 18th of that amount of charge. And this is what will be equal to the elementary charge, the charge of a single proton or electron. And if you do the math, that works out to this famous number, 1.6 times 10 to the negative 19 Coulomb. So every electron or proton carries this many coulombs of charge. Okay? Personally, I think they should have made this equal to 1, but then we'd have to deal with gigantic numbers all the time. So I feel like maybe that's the deal. But the thing is, this is such a massive amount of charge that, you never really deal with it. Like, for instance, you might get 1.5 coulombs passing to Earth in a lightning strike, right? It's an incredibly large amount of charge. But this is the elementary charge, okay? And this is the number of charges that make up 1 single Coulomb. All right, let's try something for fun. Let's say you have a mole of electrons. How much charge do I have? So we can actually derive our own little formula here for that. We can say that Q, the amount of charge, should be equal to N, the number of things we have, times the charge on those things. Okay, so in this case, the N value, that's the number that we have, that's 6.02 times 10 to the 23, and it's electrons. So each one has negative 1.6 times 10 to the negative 19 coulombs, and you do that multiplication, and what do you get? So you get roughly about 9.6, so 6 times 1.6 gives you about 9.6, 23 plus negative 19 times 10 to the 4 coulombs. And yes, this is negative charge, so we can call it negative. Remember that coulombs can be either negative or positive depending what the charge carriers are, okay? So Q equals NE is a formula that you might need, okay? I don't really think you actually need it because it's just common sense. If I have this many charge carriers and each charge carrier carries this much charge, the total charge is just not the sum of those, but the product of those, the product of them. All right, so let's go back to Coulomb's equation then, which says that the force, either attractive or repulsive, is equal to KQQ over R squared. So before we figure out what or learn what this actual value is, what units does it have to be in? Looking at what else we have here. So we've got C's and C's, and we've got M down here. So what units does K have to be in terms of? Okay, so it's got to have newtons. What else? It's got to cancel off. There you go. Okay, so there's your base. Well, it's not quite your base units actually, but it's a convenient set of units to think of, right? Here's an interesting fact. A Coulomb is not a base SI unit. It's not. You'd think it would be, but it's not. The base unit of electricity is actually the amp. So you actually define the Coulomb in terms of amperes, all right? So 1 Coulomb is equal to 1 amp second. So what does that mean? Well, later we'll learn about flowing charge, or you might already know about it. But as charge flows, we measure the flow of charge in terms of a unit called amps, which is a fundamental unit. And if you run a 1 amp current for 1 second, the amount of little pixies that come out the end is equal to 1 Coulomb. Or in other words, another way to think about that is you get that this number of electrons flow every second in a 1 amp current. So 6.25 times 10 to the 18 little pixies come flying out the end. So 1 Coulomb of charge flies out the end of this hose every second. Now, I mean, obviously that's not really how it works. It's got to be like a completed circuit, you know, if you have like a battery. But if you have a 1 amp current and you run it for 1 second, 1 Coulomb of charge gets transferred through the system. So yeah, so I sort of glossed over this. Here's another way to write it. Okay, so Q, the amount of charge, is equal to I times T. So what does that mean? Well, it means Q, the amount of charge. Charge is always shown as Q. That's by convention. Current is shown by I, and time is shown by T. Okay? So if I have a 1 amp current for 1 second, 1 times 1, I get 1 on this end, and this is the Coulomb. So the unit of coulombs is just the SI units combined. So it's the amp second. Okay? And that's called a Coulomb to honor Mr. Coulomb. Similarly to how the kilogram meter per second squared, we just call that a Newton to honor the Fig Newton, the most delicious snack of all time. So now the last thing that we need to discuss here is what actual value, what is this coefficient or what is this constant equal to in actual numbers? And it turns out that whereas G, which filled the same role when we were talking about gravity, was extremely small, K is huge. It's huge. And the value of K is this. It is 9 times 10 to the 9. So it's 9 times 10 to the 9 newtons inverse coulombs meters squared. So let's do an example problem. E, a G. How much force, maybe this will illustrate the size of a Coulomb too. How much force would you find if you were to have 2 1 Coulomb charges set 100 meters apart? Actually, even better here. Let's make this even better. See this. So to have 1 Coulomb charges set 45 centimeters apart on either side of you. All right, so this is not very realistic. This could never happen in real life because with that amount of charge, you'd just like arc right through the air. But just for fun, let's pretend. So here's one. Here's the other one. Oops, let's make them the same size. Does it bother you if I make my circles not equal? Couldn't care less. Okay, and let's put you in the middle, just for fun. Worst drawing ever. Okay. Question 45 centimeters. This person's very narrow. Okay. What kind of force would they expect to have on them? Is it a lot or a little bit? So the force is equal to KQ over R squared. All right, so we've got 9.0 times 10 to the 9. We've got to have our coulombs cancel off. We've got to have our meters cancel off. We got to be left with newtons. We've got 1C. We've got 1C. Now, as far as dealing with the positives and the negatives, you don't really do it that way. It's either attractive, right, if they're opposite forces, or it's repulsive if they're the same. That's all you really need to worry about in terms of that. So you don't start putting your negatives and positives in here. You just understand the scenario. And then that's divided by 0.45 squared. Assuming we could prevent these from arcing across and like shooting lightning bolts across this dude, how much force would these balls exert on each other? I'm going to get like 4.4 times 10 to the 10 newtons. If you want to make that like an equivalent in like kilograms, I guess, divide it by 9.8 or roughly 10. So about 4.4 times 10 to the 9 kilograms. So like 4 billion kilograms of crushing force on this guy. So he's probably not gonna survive that, I don't think. Yeah, he totally wouldn't feel it because he'd be squashed instantly. Unless maybe he's like some sort of superhero. Like maybe he's the Hulk. Let's give him like Hulk features. I'm gonna give him jean shorts that are a little bit faded. This is when he's just turning to the Hulk from Bruce Banner. Okay, so that's what's happening there. Okay, so I guess we'll kind of leave it at that today. That's probably enough. We'll talk about fields a little bit more going forward, but just remember, fields are areas around charged particles where other charged particles experience force. Fields are always drawn based on the force applied to a positive test charge. So no matter where I put my test charge around this object, that Fe will always be away. And now we have a way of figuring out what that actually is using Coulomb's law.